Good morning, ma'am. My name is Tinishwar, son of Madhivanan. My metric number is 10DEE20F2044. So now I'm going to present about presentation 2, which is cost of DEE20023 of semiconductor devices. So now I'm going to start. Okay. For question 1, sketch and label the schematic symbol for an MOSFET and explain its operation. Okay. Here is the schematic diagram of E MOSFET, which means D is drain and G is gate and source S is source. Yes, sorry, it's merely missing is SOURCE here. So we call it E MOSFET is enhancement MOSFET N channel, right? So I explain about the E MOSFET. So when an E MOSFET is zero bias, there's no channel between the source and the drain materials. Thus, IT equal to 0 ampere, which means a positive induced channel is E MOSFET with a positive voltage on the gate. The P substrate is made for more conductive, and TGS exceed the threshold voltage rating for components and voltage a channel is formed. This allows to current to pass through the component between E MOSFET used to primarily switching devices that operate at cutoff or in the ohmic region. The question 2 is about the explain the characteristic of the UJT. So here is the gra- uh, graph of the UJT, which means the static emitter characteristic for UJT. So here is the cutoff region, and for from IP to IB is the negative resistance region, and after IB is the saturation region, and here is valley point. Um, so here is peak point, right? And by emitter current IE, right? So so the static emitter characteristic is a curve showing the relation between emitter voltage VE and emitter current IE. Of a UJT at a given interface voltage, VBB is shown in the figure. From figure it is note that for emitter potential to the left of a peak point, an emitter current IE never exceed IE, and the current IE is correspond very closely to the reverse leakage current IC of the conventional BJT. And this region, as shown in the figure, is called the cutoff region. And once conductance is established at VE equal to VP, the emitter potential VE start decreasing with the increase in the emitter current IE. This corresponds exactly with the decrease in the resistance RB for increasing current IE, and this device therefore has a negative resistance region which is stable enough to be used with a great ideal of reliability in the areas of application listed earlier. Eventually, the valley point reach and any further increase in emitter current, i.e. places the devices in the saturation region as shown in figure. So, moreover, this is the point that we have to talk, which means the peak point emitter current, it is the emitter current at the peak point, and it is represent the minimum and the current that is required to trigger the device UJT, and it is the inversely proportional to the interface voltage VBB. And valley point voltage is the emitter voltage at the valley point, and the valley voltage increase with the increase in the interbase voltage VBB. So finally, there was the valley point current. The valley point current is the emitter current at the valley point, and it is increase with the increase in interbase voltage VBB. So that is the end for presentation 2, man. Thank you, man.